Alrighty. So, what is a limit? Okay, so in calculus, your first exposure to limits is typically seen as something like this right here. So you have some function of x, and it's a rational function in this case, x squared minus 1 over x plus 1. You know from your experience with rational functions that the domain of the rational function is all real numbers except where the denominator is 0. So in this case, it would be x, it cannot be equal to -1, right? Because if x were to equal -1, then it would be undefined. But if you were to plot it out like x squared minus 1 over x plus 1, you would see, like on the graph, it kind of looks like a line. From this side, it's approaching something, and from this side, it's approaching the same thing. So mathematically, you would write that out as the limit as x approaches, in this case it's -1, but it does so from the left side. Yeah, so it approaches from the left side, which is what this negative sign is. It's coming from the negative part of the x-axis, equals, in this case it would be -2, or no, 0, I believe. Right, 0. And then also, if you approach it from the positive axis here, from this right side, it approaches 0 as well. So you'd write that as limit as x approaches -1 from the right side, right, the positive side of x, equals 0. So what happens whenever your limit from your left side and your right side is the same is that you write it out in general form like this. You say limit as x approaches -1, and note that I'm not saying from the left or the right this time. I'm just saying as it approaches -1. So that means either from the left or from the right, doesn't matter, it still approaches 0. And I'm not writing it out here, but I am meaning to say limit of f of x. So there'd be like an f of x here equals 0. And for rational functions like this, normally what you could do, and I was right, it would be -2, by the way. So for instance, x squared minus 1 is the same as x plus 1 times x minus 1. And you can go ahead and kind of multiply that out, and you'll see that it does result in x squared minus 1. But because we have an x plus 1 in both the denominator and the numerator of the fraction, you can go ahead and cancel them out. And so you're left with kind of like a function that's fixed. You repaired it. You repaired the hole inside of it. So now there's no longer a hole, and this kind of carries since the hole is repaired, it's now just a straight line. And so the limit's not really necessary. But that's one use of the limit. So whenever you have kind of like a discontinuity in your graph, for instance, let's say you had a regular smooth graph and it just happened to be undefined right here, if it approached the same thing from the left and it approached the same thing from the right, then you could say the limit as x approaches, we'll say a, and we'll call this point a. We'll call this point AB. This kind of undefined point of f of x, sorry for the poor handwriting, equals b. But that only holds if it approaches the same thing from both the left and the right. So the limit as x approaches this x coordinate is this y coordinate, is what you'd say. Sometimes you don't take the limit as x approaches a, you take the limit as x approaches infinity, for instance. So, and same thing for negative infinity, but infinity works just as well in this case. So what you kind of do is you imagine the behavior of the function as x grows and increases like infinitely. So you can kind of see it just visually. That is, x grows, it steadily approaches but never touches 0. And you can kind of imagine that as in 1 over some very big number squared, like 1,000 or 100 squared. 1 over 100 squared is a very small number. And 1 over 1,000 squared is even smaller, even closer to 0. But once again, not quite touching 0. Right? So as x increases, it approaches 0. So whenever you say the limit as x approaches infinity of this particular f of x, 1 over x squared, you say that its limit as it approaches infinity is 0. Sometimes limits don't exist. So I mentioned that the limit only counts, or it only exists, if they approach the same thing from the left and the right. You see here this graph of x over the absolute value of x. So for negative x's, it's some negative x over some positive value of absolute value of x, right? The absolute value of x is always positive. So you have some negative value here, -1 to be precise, and you have some 1 to be precise. Now this function is not defined at 0. Why? Because if it were, then you would have 0 over the absolute value of 0, which is 0, which is just undefined, right? It doesn't exist. So typically, as seen up here, in order to kind of patch up or kind of make up for any discontinuities, you would just take the limit to see what they both approach. So we can go ahead and see the limit as x approaches 0, this time from the left. So you kind of follow the function, blah, 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 and you see, oh, it approaches -1. Now, if you do the same thing again, but approaching from the right, x approaching 0, but from the right, blah, 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 you follow it along, you end up with 1. You see, the limit from the left and the right are not the same, and so the limit as a whole does not exist. So that was a very basic introduction to limits. They kind of are what a function approaches from the left and right if they exist. Sometimes, if it's a rational function, you can kind of patch it up. If it's asking you something like limit as x approaches infinity or negative infinity, you kind of imagine what kind of behavior the function takes as you get increasingly bigger and bigger numbers, or increasingly more negative and more negative numbers. And if the limit from the left and the right are not the same, then the limit does not exist. Another thing are things that don't really... Ooh, that was a terrible graph. Another thing are things that don't really have like defined limits. So like a trig function kind of looks like this. There's not really a set value it takes as x approaches infinity. It kind of oscillates forever and ever and ever. So whenever you say the limit as x approaches infinity of cos of theta, or cos of x, for instance, that limit does not exist either, because it doesn't actually converge on any kind of value. That's what you need to remember. The limit only exists if it converges on a specific value. Now, depending on where you are in calculus, you might be learning about derivatives, which kind of is stated like this: the limit as h approaches 0 of f of x plus h, that's an h, not an m, sorry, minus f of x over h. Now, you asked me about limits, so I'm not going to go over this, but do note that the limit is a central topic in calculus because it's used in pretty much the definition of every important thing, including integrals and derivatives and infinite sums. So it's useful to kind of have an intuition for what a limit actually is. And in most cases, especially in single variable calculus, the limit simply means see what the function approaches as your x value or your h value or whatever value approaches some constant, or kind of see what kind of behavior your function has as you approach some end, either negative infinity or infinity. And if they don't match, then the limit does not exist at all. The end.